All right, this is 3-1. We are starting probability, so there's a couple things we just need to make sure that we know before we really get into it. So how many cards are in a standard deck of cards? So a lot of probability questions revolve around decks of cards, and I found that a lot of kids don't know these basic things about cards. So we're just going to make sure we lay these ground rules first. So in a standard deck of cards, there are 52 cards. How many suits are in a deck of cards? There are 4 suits, okay? You have clubs, spades, hearts, and diamonds. Clubs and spades are black. Hearts and diamonds are red. Okay. How many of each number or face card is there in each deck? There are 4. Like there are 4 2s, there are 4 queens, there are 4 aces, whatever it is, because there's 1 of each suit. So there is 1 queen of hearts. There is 1 2 of spades or whatever. All right, so basic probability. It's really simple today. It's just really how many of the thing you want do you have over how many total things do you have. So the outcome is the result of a single trial in your experiment. So whatever you actually get is your outcome. The sample space is all of your possible outcomes. So if you're drawing from a deck of cards, your sample space is all 52 cards. If you're drawing a card, it could be any one of those 52 cards. The outcome is the card you actually pick. An event is 1 or more outcomes. So like you want to draw a club. So your event is to draw a club. Okay. So here's just kind of breaking it up. So rolling a 6-sided die. So if you're rolling a regular 6-sided die, your sample space is a 1, 2, 3, 4, 5, or 6 because those are all of the numbers that you could roll on the die. Okay. An event is what you want. Okay, so an event is what you want to happen. Okay, and then the outcome is what actually happens. So the event, again, what you want to happen, like rolling an even number, would be a 2, a 4, or a 6. And then the outcome, you actually roll the die and see what happens, and you rolled a 2. So a simple event means there can only be one outcome. So like you want to roll a 4. That's it. Your only outcome could be to roll a 4. Okay? A non-simple event, rolling at least a 4, so like 4 or more. You could get a 4, a 5, or a 6. That's not simple because you can, more than one thing fits the criteria. So simple, only one thing will work. Not simple, more than one thing would work. All right, theoretical probability is what you think is going to happen. This is what you normally would focus on. So theoretically, if you roll a die 6 times, you should get 1 of each number because you have a 1 out of 6 chance of getting a 1. You have a 1 out of 6 chance of getting a 2. So theoretically, if you rolled it 6 times, you should be getting 1 of every number. Okay, that's not usually the case, but in theory, that's what should happen. It's the number of outcomes divided by the total outcomes in a sample space. Okay, so how many times do you roll a 1? How many times do you roll a 2? Or like how many 1s are on the die? How many 6s are on the die? So theoretical, again, is what you think should happen in theory. We'll get to experimental probability is what actually happened. So if you really rolled a die 6 times, what happened versus what did you think should happen? So theoretical probability, so you roll a 6-sided die, find the probability of each of these things. So rolling a 3, how many 3s are on a die? 1 out of how many sides are there? 6. That's it. Okay. Right now, like if it's easy to put as a fraction like that, just leave it as a fraction. You don't have to divide it out. Event B is rolling a 7. How many 7s are on a die? None. Out of how many sides? 6. There's a 0% chance of rolling a 7. It doesn't even exist. Event C is rolling a number less than 5. Less than 5. Okay, so that would be a 1, a 2, a 3, or a 4. Okay, so that's 4 numbers out of 6 sides. And you can leave it 4 out of 6, that's fine. If you want to reduce it to 2/3, you can, but honestly, I'd probably rather you leave it like this because it makes more sense to the actual question. Okay. All right, I'll do these with you because people struggle with cards. Selecting a 7 of diamonds. There's only one 7 of diamonds. There's 4 7s, but they're all different suits. So there's only one 7 of diamonds out of 52 cards. So you only have a 1 out of 52 chance there. Selecting a diamond, okay, a quarter of the deck is diamonds because there's 4 suits. So you could do 1 out of 4 because a quarter of the deck. Really, you have 13 of every suit out of 52 cards. Okay, there are 13 diamonds out of 52 because 52 divided by 4 is 13. Okay, probably a good thing to know, 13 of every suit. Okay. Selecting a diamond, a heart, a club, or a spade. So any of them will work. Diamonds, hearts, clubs, and spades. That is all of the suits. So that's all of the numbers. Okay, or all of the cards. So that's 52 out of 52. Or 100% chance. You have a 100% chance of picking a club, a heart, a diamond, or a spade. Okay. All right, statistical, empirical probability, experimental probability is lots of different names for it. So you actually do something. So you say you actually roll a die 17 times and you count how many 1s, 2s, 3s, 4s, 5s, and 6s you get out of those 17 times. Okay, you actually do it based on observations obtained from experiments. Okay, you really do it. So then how many times did you roll a 6 divided by how many total times did you try? So you rolled it 3 times out of 17 or whatever. So this is what actually happens. Theoretically is what you think should happen. Experimental probability is what happens. So this says that a pond contains 3 types of fish. Every fish is equally likely to be caught, and you catch 40 fish each time and release it back into the pond. Okay? So bluegill, redgill, crappie, these are your different fish. So you put your line in the water and you catch a fish 40 times. And you write down what kind of fish it is each time. Okay, so of those 40 times, you caught 13 bluegill, 17 redgill, and 10 crappie. So that's a total of 40. You didn't guess that that's how many. You actually did that. Okay, you actually caught that many fish. Okay. So it says if you catch another fish, what's the probability that it's a bluegill? So you're going to use this information that you have to guess how many. So you use your experimental probability to guess. So how many bluegill did you actually catch? 13. Out of how many total fish did you catch? 40. So you have a 13 out of 40. Based on what has happened in the past, you have a 13 out of 40 chance of picking it. Okay, you're going to leave it 13 out of 40, but if you want to, you can divide it out. Okay, so 0.325 chance. So experimental probability, you actually ran the experiment, this is what happened, versus theoretical, this is what should happen. Okay, an insurance company determines that every 1 in 100 claims, 4 of them are fraudulent. So what's the probability that the next claim is fraudulent? They actually looked at them. There were 4 out of every 100 that happened. So this is 4 out of 100 is your chance, or 0.04. Now, law of large numbers is important in actual statistics. So you have a theoretical probability. Like we said, you roll a die 6 times. Theoretically, you should get 1 of every number. Usually does not happen like that. But if you rolled it 600 times, you would probably have 100 of each number. It would be a lot closer to that 1 out of 6 the more you repeat the experiment. Okay? So if it's repeated over and over, the empirical probability approaches your theoretical probability. So what's actually happening gets a lot closer to what should be happening the more you do it. So roll a die 6 times, not that likely to actually get 1 of every number. Roll it 600 times, it'd be a lot more likely to have around 100 of every single number. All right, so here are these employees' ages and how many people in this company fall into each of those age categories out of 1,000 total people. So if you are being asked to find somebody, so that means the probability, this P always means probability, and then the parentheses is what you're finding the probability of. So the probability of somebody ages 25 to 34. So here's my 25 to 34 category. How many actual people are in that category? 366. Out of how many total people are there? 1,000. Okay, so how many people in the category over how many total people there are. A complement is the opposite. So the probability of something not happening. Okay, and we write it with that little tick mark E prime. So if I say P prime of picking a heart, okay, that's a probability of not picking a heart. Well, a heart is hearts are 1/4 of your deck, so the probability of not picking a heart is 3/4 of your deck. So the probability of not doing something, it's just the opposite. So the probability of doing something, so the probability of picking a heart, and plus the probability of not picking a heart is going to be 100%. Okay, so the probability of doing something and not doing it is 100%. Or 1. All right, so P not of 25 to 34. So the probability of not picking somebody in that age group. So we said that the probability of doing it was 366 out of 1,000, correct? So the probability of doing it, of 25 to 34, was 366 out of 1,000. Okay. So the probability of not doing it is going to be 1 minus 366 over 1,000, because 100% is 1. So I did it with decimals instead of fractions, but it's the same thing. So 366 over 1,000 is 0.366. So 1 minus 0.366 is 634. Okay. You also could have added up all of them or taken 1,000 and subtracted 366, gotten 634. There's a lot of different ways to do it. It's just the probability of not doing something, so it's everything but that. So this says the probability of not picking a red gill. So if we go back up to the fish example, I picked 40 total fish, okay, and 17 of them were red gill, okay? So the probability of not picking it is going to be 40 minus 17, which is 23 out of 40. So that's the probability of not picking it. Or I could have added 13 and 10 and gotten 23. It's the same thing. It's just not including whatever was listed. So not red gill is 23 out of 40. Okay? All right, 3-1.